going to talk about Bernoulli's equation and how it is implemented one way into the engineering field. As you can see, Bernoulli's equation is first pressure over rho times gravity plus velocity squared over 2 times gravity plus z equals a constant. As you can see, the first term of Bernoulli's equation is referred to as the pressure head. The second term is referred to as the velocity head. And the third term is called elevation head, or also referred to as static head. And they're all equal to one constant. Bernoulli's equation can also be written as such. Today, we're going to use this derivation of the equation in order to solve a problem in the engineering world. By using this equation in this form, we can solve for one variable and show how it is affected by other factors of the equation. We are now going to talk about Bernoulli's equation and how it is implemented into the engineering field. Have you ever wondered how airplanes take flight? Well, if you were wondering, this is a question that can be answered by Bernoulli's equation. I want to begin with a Bernoulli equation example with respect to airplanes. Once that is completed, I'm going to do a small scale experiment that also introduces you and shows you Bernoulli's equation in real life. Okay, in this diagram depicted is an airplane wing, which is the black portion. Going towards the wing is a streamline, and you can see the air particles split into two, the upper streamline and the lower streamline. The upper streamline shows you low pressure, high velocity. The lower streamline shows you high pressure, low velocity. So in order for an airplane to take flight, you must first have this dynamic. When the air pressure underneath the wing is high and the velocity is low, the airplane then can take flight, which in turn is called lift. This dynamic is used widely throughout the engineering field, spanning from how an airplane wing is designed to how a car is designed in order for it to stay on the ground. We are now going to complete a Bernoulli equation problem. Given this information, we are going to calculate the lift of an airplane. Okay, in step 1, we will first show Bernoulli's equation. Then in step 2, I have canceled out rho, g, and h, which is the gravitational energy. It is negligible in this problem. Step 3 is what we get after we cancel in step 2. In step 4, we do a little manipulation to get P1 minus P2, which is P net. And P net here equals F net over area. If you go back previously, you will see where we got F net from. In this problem, F net equals lift. So P net equals 1/2 times rho times V2 squared minus V1 squared. We get rho as a given, V2 as a given, and V1 as a given. By simply completing the multiplication, we get that P net equals 18,646 pascals. Now we will take the P net that we received before and implement it into this equation. By algebra, F net equals P net times area. We are now going to take the P net we just received from step 7 and multiply it by the area that was given. If we do this simple multiplication, we will get that F net equals lift, which equals 1,491,680 Newton force. And this is a simple way that engineers calculate the lift force on airplane wings. Here's an experiment of Bernoulli's equation with real life. I'm going to transfer this ball into this cup without tipping the cup, lifting the cup, or lifting the ball.